What happens in WDM links? How do you do dispersion compensation for WDM links? What is a WDM link? A link which carries multiple carrier frequencies across the C-band. We talked about it earlier. Typically, there are 80 channels covering the C-band. So, if you're designing the dispersion compensating fiber, the dispersion compensating DCF should actually compensate for the entire span of wavelengths. It is the same DCF which should compensate for the entire span. You can't keep putting one DCF after the other when different fibers are, different wavelengths are being used in the system. So how do you do that? So instead of doing D1L1 plus D2L2 equal to 0, we need to now make sure that D1 at all the lambda ends that you are using in the communication system, L1 plus D2 at all the lambda ends must be equal to 0 for all the ends. N represents the number of channels, and let's say we have 80 channels in our system. So again, we can do an approximation saying that across the C-band, the D is almost linear across the C-band. So this is 1 to N, and C-band typically is from 1530 to 1560 nanometer. This is a ballpark number. The exact value is around 1528 to about 1566 nanometer. Essentially, it covers 80 channels with a channel spacing of 100 gigahertz each. So if it's assuming that this is almost linear, then I can write D1 at any lambda n, so this is, let's say this is lambda n, and this is D1 at any lambda n. And if this is linear, I can calculate this as D1 at center wavelength. This is D1 at center wavelength plus S1, the slope, times lambda n minus lambda c. So this is lambda n wavelength, and this is lambda c wavelength. So assuming it's linear, you can calculate, you can relate D1 at any lambda n this way. I can substitute this in the previous equation. I can do the same thing for the DCF also for D2, and substituting this equation. Then it turns out that rather than the D1s and D2s getting related, it is the slopes that are getting related for the SMF and the DCF. So if you want to ensure that all the colors in a WDM channel are compensated in the same way, instead of ensuring D1L1 plus D2L2 equal to 0, you need to ensure S1L1 plus S2L2 equal to 0. So you have to basically use the dispersion. Of course, don't think that it is independent of D1, because S1 is actually a function of D1, right? So S1 is nothing but the first derivative of D1. Similarly, S2 is the first derivative of D2. So the point is S2 is minus S1 times L1 by L2, but of course L1 by L2 is D2 by D1. So you could actually use this relation to now compensate for the dispersion of all the WDM channels. So this also gives you a nice relation. S2 by D2 is S1 by D1. So if we can satisfy this relation, the dispersion compensation for WDM link can be carried out simultaneously with the same DCF. Now we need to see what are the limitations of the DCF based compensating system, and why do we need another method for compensating, because DCF seems to be a very effective way of compensating dispersion, because all it involves is introduce a fiber in the whole link, right? But turns out that as we discussed earlier, altering the waveguide dispersion leads to much smaller core diameters. And when you have core diameter smaller, what it means is that the diameter of the core is smaller. You will have more fraction of power in the cladding than in the core. So it will lead to a larger loss. It will lead to more bending loss and so on. Intensity, when the diameter is smaller, the area is smaller, intensity of light in the core becomes larger, and large intensity means large nonlinear effect. That will be clear in the next module, but for now let's understand that large intensity means large nonlinear effects. So DCFs will have a much lower threshold for nonlinearities than in a SMF. It's not bitrate scalable. You cannot use the same DCF for all the bitrates. Reason? The tolerable values of dispersion become very small, And what happens is that even for very short length of fiber, you would need dispersion compensation. When you have smaller pulse width, the spectral content becomes larger, and the larger spectral content would mean that the pulse accumulates a larger phase. So which means that the same length of DCF will not be able to compensate for your entire length of the fiber. So these are, in these cases, you cannot use the same DCF. You cannot, once you have designed the DCF, it will remain fixed as far as the pulse width, the repetition rate goes. So which is a very limited design. So the other major difficulty as far as the optical networks is concerned is you cannot make your network path reconfigurable. You cannot make your network, it cannot keep changing paths because the length will be different, so the required DCF could be different. So for a modern networks, over the last 10 years, what has happened is dispersion compensation is not done using DCF, it is done using digital signal processing. So we typically use an analog to digital converter to convert the signal from the analog domain to the digital domain. So essentially at the output of the receiver, after the photodetector, you get your analog signal, you digitize it. So for every sampling instant, you have a sequence of 0 or 1 depending on the number of depending on the vertical resolution of your ADC. So you have basically digital sequences. Once you have digital sequences, you can use digital signal processing to compensate for the dispersion. So the entire filtering process is not done in the DCF, it gets done in the digital signal processing at the output of the fiber, after you do the reception. So we know the propagation model is this, considering the second order dispersion. The transfer function is this, considering the second order dispersion. So the frequency domain equalizer, which will compensate for this phase, is e power minus j half beta 2 omega square z. So this is the block diagram for digital compensation. So what you do is, your received signal will have a sequence x of k corresponding to the digital samples of the whatever signal that you received. So remember, you're not using any dispersion compensating fiber. You're allowing the signal to accumulate the dispersive phase. You receive as it is, convert it into digitized sequence. You have digital samples, and those samples are represented by this x of k. Those samples are represented by x of n. Let's say x of n represents the received sequence. You do a Fourier transform of that, you do an FFT of that, you get x of k. So you have basically converted your time domain sequence to a frequency domain sequence, and you know what is the filter, which is an all pass filter corresponding to dispersion dispersive system. So you can actually do Ck corresponding to discrete time equivalent of this. So your Ck multiplied by Xk, Ck is corresponding to this, and Xk corresponds to the FFT of your x of n. So you get your x prime k, which is actually a compensated version of the signal in the frequency domain. You go ahead and find the IFFT of this, inverse Fourier transform of this, you get back your compensated signal. So all what you're doing is, you're allowing the system, the signal to, so from the transmitter, you receive as usual, do not do any dispersion compensation. Doesn't matter what is the length of the fiber that you have used. Then you take it through an ADC. So you get your x of n. Once you have your x of n, you calculate your x of k by doing a Fourier transform. Then you apply this filter, all pass filter. Of course, while applying the all pass filter, you should know the z, what is the length of transmission. You should know what is the length over which the signal has transmitted. So that will help you understand what is the phase accumulated. So from that, you calculate, you apply this filter, apply this C of k times x of k, because it's a frequency domain equalization, is just a multiplication here in the frequency domain. So you get your corrected signal, and then you do your IFFT operation to get back your original signal. So this is the process that is done throughout the current installation. All the current new installations actually do this signal processing, or all the upgraded systems where the DCF is not sufficient to compensate for the dispersion. This is the process done. Of course, different implementations of this equalization is possible. What I have explained is a frequency domain equalization. You can also use a time domain equalization. Those who have learned a basic DSP course will recognize that you can also do a multi-tap filter to compensate for the dispersion in the time domain as well. So that is what is used in the current systems. So with that, we complete the module on dispersion compensation. The next module is going to be on fiber nonlinearities.